Hello. So in the last video we got here where we are developing equations for the interior nodes. Okay, so I take it that you understand how these are developed. So again, what we do is that you move all the interior points that you find here to the right hand side of the equation. And so if you do that, what you get is you get this set of equations. So Q6 and Q16 are on the boundary, so you can move them to the right hand side. When you do that, you can rewrite this whole thing as a matrix, so that the left hand side you get this coefficient matrix here multiplied by the values of phi, and then to the right hand side you have the known boundary points, which are given by this. This is written in such a way that you can apply a general Dirichlet boundary condition to it. So once you know the points at the boundary, this becomes more general. So all you need to do is get this, write a nice code that can give you this matrix, and then just concentrate on this, right? Once you have the nodes, you can develop this right hand side. Okay. So let's take these boundary conditions. Okay, so you suppose that the boundary conditions are given by this. So this is the same domain that we are looking at. On the x equals 0, that is along this, if you like, along y, phi is equal to y. Okay, so phi is equal to y on x is equal to 0. Now along y, we only have 3 intervals, so if you divide 1 by 3, each will be 1/3. So this is 1/3, this is 2/3, and that is 1. So if phi is equal to y here, it means that on this node phi is 1/3, here phi is just 2/3, here phi is 1. And then on y equals 0, that is along the x, phi takes values of x. Now in this case, because the intervals are the same, we have 0, you have 1/3, 2/3, and 1. So here the value of phi will also be 1/3, 2/3, the value of phi will be 1, based on this condition here. Then on the top boundary condition, any point here along here phi is 1, and then on the right hand side boundary phi is also equal to 1. Okay. So we have all the boundary conditions covered. We have the top, we have the right, we have the bottom, we have the left boundary conditions. So these are given by this. So all you do now is that you go back to the equations and apply the boundary conditions to the system. Note that we got the system. So all you need is get 0.6 and 16 and add them up, 13 and 15 and add them, and so on. Okay, so if you do that, the right hand side vector becomes this, because phi 6 plus phi 16 will be 1/3 plus 1/3, which is 2/3, right? So if you go back, 6 is this guy, which is 1/3, 16 is this guy, which is 1/3. So if you add them, you can get 1/3. Know that this is 1/3, that is 1/3. And so that is what gives us 2/3 here. You do the same for the other ones. Get 5/3, 5/3, and then finally you get 2 for this. So you plug this to the right hand side and you have this system of equations. So now this is as easy as it gets, right? You have your coefficient matrix, you have your unknown interior points, that is phi 1, phi 2, phi 3, phi 4, and then you have the right hand side. So you can basically represent it as this, and you can solve phi using that. Okay, so if you just solve this, right, solve for phi from this, right, find the inverse of this, multiply by that, you get your phi, you get the solution. So this is simple, but the point is to take you through the process and the steps that you can use to obtain a solution for this simple elliptic equation with Dirichlet boundary conditions. Later on, we'll talk about the efficiency of solving this. Instead of solving this directly, right, we have more efficient methods. I'll talk more about that later on. Now for now, we'll look at a second example where instead of the Dirichlet boundary conditions along the boundary, we are going to have a Neumann boundary condition on one of the boundaries. The point is just learn how you treat Neumann or derivative boundary conditions, okay, for elliptic equations. So we'll start with example 1 and then we'll move on to other ones. I mean, second example 2. So again, we want to look at the Laplace equation. In this case, x is from 0 to 2, y from 0 to 1, all right? And then we'll split it as shown here, okay? So this has 4 intervals, okay? Which means I'll just take 2 and divide 2 divided by 4, and then I'll get the length of each. So x is 0 here, the x is 1 over 2, 1 2/3, 3 over 2, and then x is equal to 2 finally here, and then you do the same for the y, okay? Now, as it is, the only interior point that that we need to be concerned about are node number 4, number 5, and number 6, okay? But we don't know node number 1, 2, and 3 because along here we are not given the Dirichlet boundary condition. We are given a Neumann condition. We are told that the phi, the y is equal to 0, so we need to treat that. But along all the other boundaries, along this boundary, phi is equal to 0. So this point is 0, phi is 0 here, phi is 0 there. Along the top boundary, phi is x. So here the value of x is 1 over 2. So phi is going to be 1 over 2 here. Phi will be 1 here, phi will be 3 over 2 here, and phi will be 2 there. Okay, then here along this, okay, phi is equal to 1. So that is phi is equal to 1 here, 1 here, okay, and then phi is equal to, of course, x here, 2 here, okay, so phi is 1 and 1. All right, okay. So let's see how you develop this. So you can basically, the processes apply the same scheme that we used for the interior nodes in the previous example to 4, 5, and 6. Okay, that gives you a system of 3 equations. And then you would have to modify this one, because note that if you want to do the same thing here, at point 1 you have the western, you have the eastern, you have the northern, but you don't have a southern point. So how do you treat that? Okay, which means to apply the system, the equation of the system of discretization equation to point 1, you have to modify it. Once we modify it, then we can apply 1, 2, and 3 to it. All right, and that will give us another set of equations. So this is how you go about it. So for 1, 2, 1, 5, and 6 is the same as we've done before. We're going to apply this so that at point 4, we're against 5p will be 5, 4, minus 5, 5, minus 0, minus 1 over 2, minus 5, 1 is equal to 0. That is because when you are here, right, note that the equation is the main point, the central point, the east, west, north, south, okay? So here, east is 5, 5, west here is 0. The value of phi here is 0. That's why you have a 0 here. To the north, phi, the value of phi is x, which is half. So you have a half. And then you have phi at 1, which you don't know yet. Okay? So that's why you have a 0, you have a half, you have phi 1. That gives you that. And you do the same thing for the node 5 and then node 6. So you have 1, 2, 3 equations, which you can rewrite. All right, if you rewrite them, you get this set of equations. Okay, 13. So if you apply this discretized equation, our equation 2, the interior nodes, this is what you get. You get the system 13. Okay, and then in the next video, I'll go through this for nodes 1, 2, and 3. That is, how do you apply the Neumann boundary conditions in order to solve the equation. Okay, so we'll get to that very soon.